In this video, I introduce Vision Language JEPA, Joint Embedding Predictive Architecture for Vision Language. Vision Language JEPA is a vision language model based on Joint Embedding Predictive Architecture, which turns expensive learning of data space token generation into more efficient latent-space semantic prediction. Here is a VL-JEPA model workflow. VL-JEPA uses X encoder to map vision inputs XV into an embedding SV as shown here. A Y encoder to map the texture Y into an embedding SY as shown here. And the predictor to learn the mapping from SV QX to SY caret as shown here, where QX is a textual query. The model training objective is defined in the embedding space as shown here. During inference, a Y decoder maps the predicted embedding SY caret into caption Y caret of image or video as shown here. VL-JEPA is trained in two stages, namely, a pre-training stage uses a large-scale caption data to establish vision language alignment, and the supervised pre-training stage obtains capabilities of caption and visual question answering. VL-JEPA is trained with triplets XV, XQ, and Y, where XV is a visual input, XQ is a textual query, and Y is a textual target to be predicted. VL-JEPA consists of four components, namely, X encoder compresses visual inputs to compact embedding, as shown here. Y encoder embeds the texture target into a latent space as a prediction target, as shown here. The target embedding is expected to abstract away task irrelevant information. Predictor maps visual embeddings to a prediction of a target with a textual query as conditioning, as shown here. Y decoder is not involved in the model training. At inference time, it maps the predicted embedding as human readable text. VL-JEPA is trained with two stages. The first query-free pre-training stage aims to establish vision language alignment on large-scale image text and video text data sets, as shown here. The info NCE loss is designed to measure mutual information from the predictor and the Y encoder by contrasting a positive sample pair against the negative sample pairs, as shown here. The second query conditioned supervised fine-tuning stage empowers VL-JEPA VQA capacities while maintaining the pre-trained vision language alignment for classification and retrieval, as shown here. VL-JEPA applies selective decoding to handle vision to text generation tasks, which is a major advantage of the VL-JEPA model benefits from a non-autoaggressive process, as shown here. Because the VL-JEPA produces a continuous stream of semantic embeddings, as shown here, a lightweight Y decoder is only activated when a meaningful semantic change is detected, namely, the local variance of embedding stream exceeds a certain threshold. As shown here, this is the embedding stream, these annotations, and this selective decoding. This has advantages over the standard vision language models, which are forced to perform expensive token by token decoding for any output, and makes the VL-JEPA ideal for real-time video analysis, as shown here, this selective decoding. For more details, please check with these references. Thank you. Bye.